We've spent the last several days talking about the photoelectric effect, and basically the photoelectric effect tells us when light or a photon strikes a metal, we get an electron that's ejected. So this is what it is. Photon causes electron. Now, if we change the photon to a higher frequency, then something happens, and if we change the number of photons, then something else happens, and we talked about that as we were going over the quiz, right? But in the end, it boils down to photon causes electron to be ejected if you're above the threshold frequency. That was discovered in 1887 by Heinrich Hertz. In 1905, it was explained by Albert Einstein. In 1908, a guy named Arthur Compton discovered another effect. Sometimes a photon, if it was really, really high energy, like say an X-ray photon struck a piece of metal, then you get an electron ejected. Really, that's just the photoelectric effect, right? Nothing new there. But sometimes a second photon would be ejected as well. So now you get two photons. We'll call it photon number 1, and we'll call it photon number 2. Now Compton noticed that the second photon, photon number 2, was less energetic. Here, let's write that a little bit differently. The energy of photon 2 was less than the energy of photon 1. So we had not only an unexpected second photon ejected, but we had an even more unexpected result in that that photon would be less energetic than the first. Classical theory, which one of the questions on your assignment talks about quantum versus classical. Classical theory is basically pre-Einstein, pre-1905. Quantum theory is post-Einstein, post-photoelectric effect. Classical theory, old-style physics, would have predicted that if we were going to get light emitted from this thing at all, then it would be exactly the same as the light that we struck it with. But that didn't happen. Okay, if we shone an X-ray photon on a metal, electron was ejected, and if a second photon was ejected, it would be unexpectedly a lower energy photon. That's the Compton effect. High energy photon strikes metal, electron and second photon with less energy than the first one is emitted. In other words, if it has less energy, it has less frequency. In other words, if it was an X-ray photon that struck it, maybe you get an an electron released and maybe ultraviolet released as well. A second less energetic photon than the first one. That's what separates this from the photoelectric effect, right? You get the electron ejected in both cases, but here you're getting something else released as well, a photon that's less energetic than the first. And as we said, classical theory, which is old-style physics, will say pre-photoelectric effect would have predicted that if a second bit of light, second photon was released, then it should have the same energy and the same frequency as the first one. There's no reason why the light should change to another frequency, but yet it did. Compton explained this in kind of a neat way. Compton said that when this photon strikes the metal and an electron is ejected, really you've got a collision taking place. It's a collision between a photon and an electron. So just like a collision in an intersection with two cars. Car strikes another car, one car goes one way, one car goes the other way. When a photon strikes an electron goes one way, a second photon goes another way. It's really just a collision, just like it was back in Unit 1 when we dealt with momentum. It's a collision in which energy is conserved and in which momentum is conserved. Doesn't sound like a big deal. We probably could have figured that out, right? It's a collision in which momentum is conserved. But here's the problem with that explanation, or at least here's the apparent problem with that explanation. If we analyze this as a collision in which energy and momentum are conserved, then it's making the assumption that photons have energy, which we know they do, E is equal to h times f, but also that photons have momentum. That's a problem, because momentum, if you remember, is m times v, and the mass of a photon is 0. So how can you have momentum when momentum is mv and the mass of something is 0? Momentum, as you remember from Unit 1, is m times v. No mass should be no momentum. We don't have any mass, so how do we have momentum? Well, we're talking about an analysis done by Arthur Compton in 1908, but it stems from an analysis done by Einstein in 1905. Einstein said that energy and mass are two different forms of the same thing. Energy and mass are two different forms of the same thing. It's like saying, in a sense at least, it's like saying ice and steam are two different forms of the same thing. You get ice in your freezer, you get steam coming out of the kettle when you're boiling water for coffee. Okay? But they're not the same thing, but they're two different forms of the same thing. Einstein said energy and mass are two different forms of the same thing. You can change ice to steam and steam to ice. You can change energy to mass and mass to energy. They're two different forms of the same thing. So although a photon doesn't have any mass, it does have energy, which is like having mass. It's kind of like saying, in my freezer, I don't have any steam, but I've got ice, which is like having steam because the ice is another form of water, just the same as steam is another form of water. Two different forms of the same thing. Einstein gave us a relationship between the mass and energy. How we can find the equivalent mass when we have a certain amount of energy, or how we can find an equivalent energy when we have a certain amount of mass. It's probably the most famous, but maybe the least understood physics equation ever. Anybody know what it is? E equals mc squared. On your data sheet, it actually says delta E equals delta mc squared. So what we're going to do here is rearrange this equation and say m is equal to E over c squared. Photons don't have mass, but photons do have energy. And because they have energy, it's like they have a certain amount of mass. It's like my freezer has ice, doesn't have any steam, but it's like it has steam because it has ice, which is just another form of steam. Photons don't have any mass, but they have energy, which is just another form of mass. So let's take Einstein's equation and find out not how much mass the photon has, but what the equivalent mass is. Kind of like what the equivalent steam is in my freezer. The equivalent mass is equal to the energy of the photon divided by the speed of light squared. Now I'm going to take that and I'm going to replace m in my momentum equation and end up with this equation. P is equal to E over c squared times v. What's v stand for? Velocity, right? Speed of whatever it is it's moving. Well, how fast is a photon moving? It's moving at the speed of light, c. So I'm going to cross off one of the c's now, and I'm left with P is equal to E over c. I'm going to rearrange that, and I'm going to end up with an equation that appears in the top right-hand corner of my data sheet. The energy of a photon is equal to the momentum of a photon times the speed of light. Here's my first equation that establishes a number for the momentum of a photon that doesn't depend upon the photon having mass, but rather depends upon it having energy, which is equivalent to mass, just like steam is equivalent to ice. Now, we're going to take this first equation here, P is equal to E over C, plug a couple of variables into that, and end up with something else here. The energy that we're talking about here is the energy of the photon, which is equal to HF. So sometimes we end up with momentum is equal to HF over C. That one doesn't appear on our data sheet. Sometimes we replace E with HC over lambda over C. Well, let's do some cancellation there to tidy it up a little bit, and we're left with P is equal to H over lambda. Here's yet another equation that does appear in the top right-hand corner of my data sheet that allows me to solve for the momentum of a photon. But this one is using the wavelength of the photon as opposed to the energy of the photon. And of course, it uses Planck's constant as well. You're always, by the way, in these problems, always going to use 6.63 times 10 to the minus 34. Always use the joules second value for Planck's constant there. Two new equations here, both allowing us to find momentum of a photon, the momentum of something without mass. If you're asked a question that asks you to find the momentum of a photon, use one of these. If you're asked to find the momentum of a proton, then use P is equal to m times v, just like you would have back in Unit 1, because a proton has mass. With mass, same as it always was back in Unit 1. Without mass, because it's light, a photon, then use one of these new ones that appear in the top right-hand corner of your data sheet. Everybody look in that top right-hand corner of the data sheet now. You're going to see 4 equations up there. The first one, E is equal to mc squared. Okay, that's where these two are derived from. The next 2 equations are these 2 equations. But then there's a 4th equation that appears in the top right-hand corner that we haven't seen yet. Delta lambda is equal to h over mc times 1 minus cosine theta. There's kind of an ugly one. By the way, delta lambda is also lambda f minus lambda I, but delta anything is final minus initial, right? That's not on your data sheet, but that's okay. This one is on your data sheet. What does that mean? Well, we know that photons have momentum. In fact, that's probably the big takeaway from this whole thing, is that photons have momentum. But we know in the Compton effect, when the light strikes the metal and the electrons ejected, and we have the second less energetic photon produced, the less energetic photon produced, if there's a change in energy of the photon, then there has to be a change in wavelength as well. If the energy of the photon goes down, which it does, then the wavelength of the photon will go up. Delta lambda is that increase in wavelength of the photon. What do these variables stand for? Well, h is Planck's constant, 6.63 times 10 to the minus 34, always that value. M is the mass of an electron, because in addition to the second photon, it's an electron that's produced. C is the speed of light. And theta, careful with this one. You get 2 things released here, right? You got an electron produced and you got a photon produced. Theta is the scattering angle of the photon, not the electron. The scattering angle in degrees of the photon. I derived for you the first 2 equations, E is equal to P times C, and P is equal to H over lambda. This is a derivable equation using 2 laws: conservation of energy and conservation of momentum. Just don't ask me how to derive it, that's all. There's 4 new equations we've learned. E equals mc squared, E is equal to P times C, P is equal to H over lambda, and then there's this big one. All of this stuff we're going to have to use. We're going to have to solve problems involving momentum of a photon and change in wavelength of the photon as the Compton effect takes place and so on. But I'll tell you what, the biggest takeaway from what we've just been talking about for the last 15 minutes, the biggest takeaway from all this is that photons have momentum. There's lots of things you have to be able to do here. But if you only remember one thing and you forget everything else, remember that photons have momentum. That's the big thing with the Compton effect, is that, I don't want to say discovery, but that hypothesis that photons have momentum. So I'm going to give you a quick little summary of something here that is going to take us to this conclusion here. Way back at the beginning of this unit, we talked about the wave nature of EMR. Now we're talking about the particle nature, right? There were 4 observations that supported the wave nature of EMR. They were refraction, diffraction, interference, polarization. Then we made the transition to the particle theory of light, or the particle nature of light. And evidence to support the particle nature of light came from the photoelectric effect. And now we have the Compton effect as well that support the particle nature of light. Photons have energy. Photons have momentum. Particle nature of light. All right, I want to do one question here, and then we'll wrap it up for the day. It says, calculate the energy and the momentum of a photon. Its wavelength is 600 nanometers. Let's circle nanometers here, because we know, regardless of what this question involves, we know we're going to have to convert nanometers to meters here. We want to find the energy, gentlemen, and the momentum of a photon that has a certain wavelength. We have known how to find the energy of this photon for some time, about a week. The energy of the photon is HF, or it's HC over lambda. Since we have the wavelength, let's use the second part of it, HC over lambda. So I'm going to say 6.63 times 10 to the minus 34 joules seconds times 3 times 10 to the 8 divided by 600 times 10 to the minus 9. Now, I could have used the other value of Planck's constant for this. When I'm using this equation, okay, I've got to use the 6.63 value. When I'm using the momentum equation, I've got to use the 6.63 value. But when I'm using the energy equation, E is equal to H times F, it doesn't matter what I use. Just determines what my answer is going to be in, right? I'm using joules right now. I'm going to get an answer in joules. Works out to be 3.315 times 10 to the minus 19 joules. Rounded, that's 3.32 times 10 to the minus 19 joules. How do I use the other value? I just would have got electron volts, that's all. If you're confused, which one I got to use? Sometimes it's 6.63, sometimes it's 4.14. Always use joules, because it always works. Now you want to find the momentum of a photon. Whenever you're thinking photon momentum, I want you to go right away to the top right-hand corner of your data sheet. There's a couple of options here. I could say P is equal to H over lambda, which, hey, makes sense. I've got Planck's constant, 6.63 times 10 to the minus 34. Always use 6.63 for this equation, over 600 nanometers, 600 times 10 to the minus 9 meters. Or I could have said E is equal to P times C, rearrange that, P is equal to E over C, and use the energy that I got from the first problem divided by the speed of light. Either one of those methods would have worked. I'll stick with what I have written down there now, though. 6.63 times 10 to the minus 34 divided by 600 times 10 to the minus 9 is 1.105 times 10 to the minus 27, Dom. Thank you. Agree with that? We're going to round that to 1.11 times 10 to the minus 27. What do you think the units would be? Well, Planck's constant is joules seconds, right? So I could say joules seconds over meters. But you know what's more common? Believe it or not, even though we're talking about photons that don't have any mass, remember kilograms meters per second back in unit 1? It's kind of weird to talk about units of kilograms meters per second when there is no mass, but it's a valid set of units and probably the one that you see most often. All right, here's your homework for tonight. Besides your assignment that's due on Tuesday, besides your unit test that's due on Wednesday, you got 3 questions on page 723 that should go fairly quickly for us, I think.